Number one, state Newton's law of gravitation. I have provided my answer about this question. This one, next question. A planet may be considered as a uniform sphere if satellite is in a circular orbit of period t around the planet at a height h above the surface. The height of the orbit can be adjusted by use of the satellite rocket engines. And this is the diagram graph. Figure 1.1 shows the variations with h of t to the power 2/3. And this is the diagram. This question, by reference to forces, explain why the orbit of the satellite is circular. I have provided my opinion, my answer about this. Okay. This is the first, and this is the second. And next question, use Newton's law of gravitation to show that H and T are related by this equation, where G is the gravitational constant and A and B are constants that depend on the properties of the planet. Okay? The gravitational force acting between the satellite and the planet, which provides the centripetal force that keeps the satellite in orbit. The gravitational force, we can writing the formula F gravity equal G times M over R squared. This M is mass of planet, this M is mass of satellite, and R is the distance from from the center of a planet and the satellite. And after that, the centripetal force required for circular motion, the formula we can writing as F centripetal equal M times V squared over R. V is the orbital velocity of the satellite. Next, for a circular orbit, the gravitational force provides the necessary centripetal force. So it means we can write in from this equation becomes Gm m over r squared, because this is force as well, this is force. It equal mv squared over r. And we can simplify if we divide it by m, left hand side divided by m, right hand side divided by m. This equation becomes, we simplify, becomes gm over r squared equal v squared over r. And after that, we can writing that v squared equal gm over r squared times r. So it's going to be v squared equal gm over r. This is the first equation. The orbital period t is, wait, the orbital period t is the time taken for the satellite to complete one full revolution. So the orbital velocity is related to the period by v equal 2 pi r over t. Now substitute this equation 1 into this equation. So it becomes it becomes 2 pi r over t squared equal gm over r. So because phi squared is this one phi squared substitute into this equation, first equation. And after that, we can simplify, becomes 4 pi squared r squared over t squared equal gm over r. And it's going to be 4 pi squared r cubed equal gm t squared, like that, because r times r squared becomes 1 r cubed, and t squared times 1 gm becomes gmt squared. Okay, let's continue. Since r equal, writing here, since r equal r plus h, okay, where r is the radius of the planet and h is the height of the satellite above the surface. So the equation, this equation we can writing, this equation we can writing like this, 4 pi squared, okay, is r cubed becomes r plus h cubed equal gmt squared. After that, divided by 4 pi squared. So it becomes r plus h cubed equal gmt squared over 4 pi squared. This one. When when a equal m, when a equal one more thing, when a equal m, m is the mass of the planet and b equal r, radius of the planet. So uh, this equation we can writing as h plus b cubed equal g a t squared over 4 pi squared, this one. Use the gradient and intercept of the line in figure 1.1 to determine values for a and b. Give units with your answer. Using gradient to find a gradient equal, if you look at this diagram, okay, I'm going to find number for gradient from this from this graph, and this is 1280, this one, okay, from this one, and then after that, this is 360, okay, and after that we can find the gradient, okay, gradient of this uh, right angle triangle. So the gradient will be like this. Look that this is the horizontally axis, okay, times 10 power 6. It's going to be like this. The gradient equal 1280 minus 360 over 12 times 10 power 6. Okay. It becomes 920 over 12 times 10 power 6. Okay. And if you calculate, the result is 7.6667 times 10 power minus 5 per meter. This one. Also, gradient we can find through cube root of 4 pi squared over g times a. So, okay, so it is 7 point, becomes the equation because this is gradient. This is gradient. It means it means this one equal this one, this number equal this number. So it becomes, wait, I'm going to writing here. Maybe you will confuse this. Keep root over g times a equal 7.667, 10 power minus 5. Okay, so becomes 4 pi squared over g times a equal, this is uh, power 3 or cube, 7.6667 times 10 power minus 5 cube. So it becomes 4 pi squared over 6.67 times 10 power minus 11 times a, okay, equal, if we calculate this number, it will be 4.510 times 10 power minus 13. So A equal 4 pi squared over 6.67 times 10 power minus 11 times 4.510 times 10 power minus 13. And it's equal 39.478 over 3.0067 times 10 power minus 23. So it means A equal 1.313 times 10 power 24 or 1.3 times 10 power 24, and the unit is kilograms. Now using intercept to find B, that intercept equal gradient times B. So it means B equal the intercept divided by gradient. Intercept is 360 over gradient 7.6667 times 10 power minus 5. And if you calculate, the result is 4.695 times 10 power 6 or 4.7 times 10 power 6 meters. So this is the radius of planet. This is radius of planet, and this is the mass of planet. So 1.3 times 10 power 4, and the unit is kilograms. B is 4.7 times 10 power 6, and the unit is meters. Number 2, define specific heat capacity. I have provided my answer for this question. Let's continue. The solid blocks X and Y are made from different metals. The blocks have different initial temperatures. Block Y is initially at room temperature. The blocks are placed in direct thermal contact with each other at time t equals 0. Figure 2.1 shows the variations with T of the temperature of the two blocks. Okay. This is a diagram. State 3 conclusions that may be drawn from figure 2.1. The conclusions may be qualitative or quantitative. I have provided my opinion about this question. Let's continue. The mass of block Y over mass of block X is equal to 1.3. The metal in block Y has a specific heat capacity of 101 joule per kilograms per Kelvin. Determine the specific heat capacity of the metal in block X. Okay, so if you look at this diagram, based on this diagram, we have the several informations about it. Okay, that I'm going to writing here for our calculations because to determine the specific heat capacity of the metal in block X, it means this graph, block X, and this graph, okay? So we need to use the principle of conservation of energy. It says that the heat lost uh, by block X equal the heat gain by block Y. Okay. Or in formula, mx times Cx times delta theta x equal my Cy delta theta y. Okay. And based on the information that for delta theta x equal 45 degrees Celsius, you can look on the diagram delta theta y equal 15 degrees Celsius and Cy equal 901 and my over mx equal 1.3 based on this information. So we can find that my equal 1.3 mx. Substitute this information, this my. Substitute this information into this formula, and it's going to be 45 mx cx, okay, equal 17,000. Sorry, calculate first of this one equal 1.3 mx based on this information times 901 times 15. Okay, so it becomes 45 mx cx equal 1, sorry, not one, 17,000 569.5 mx. The calculation 1.3 times 901 times 15 is which one? 17,569.5. After that, divide by mx. If divide, it becomes 45 cx equal 17,569.5. So it means Cx is the specific capacity, 5 over 45. And the result is 390.433, so on, comes 390. Yep. And the unit is 1. Let's continue to number 3. State what is meant by the Avogadro constant. Okay. In my opinion, the number of particles such as atoms, molecules, or ions in 1 mole of a substance. And Avogadro constant has value of this value 6.022 times 10 power 23 particles particles per mole. Okay, the numbers is that one. State the relationship between the Avogadro constant Na, the molar gas constant R, and Boltzmann constant K. Okay, the relationship is given by the equation Na equal, okay, here, Na equal R over K. R is the molar gas constant and K is the Boltzmann constant. Okay, let's continue. To samples X and Y of ideal gases are both at the thermodynamic temperature T. Sample X has volume V and consists of n molecules of each mass m, lowercase m. Sample Y has volume 2V, it means twice than X, 2V, twice than V, and consists of 2n, twice than n on particle X. Each of mass 2m, it means twice as well from m. Complete table 3.1 by giving expressions in terms of sum or all of n, m, t, and phi, and the constant for in the previous information for the quantities indicated. Pressure sample X. Sample X is nkt over phi. Okay. Sample X and sample Y also it has the same over V. Why? Because it behaves as an ideal gas. Okay, the same ideal gas. So next for amount of substance, this is N over N A. Sample Y has twice the number of particles N, so it's going to be 2N over Na. Sample X mean square speed of molecules. It is 3 kT over m. Sample Y, molecules are twice as heavy to m if you look on the previous information. So if we compare with sample X, so it's going to be 3 kT over 2m. And internal energy, sample X. Sample X, it has 3 half NKT. Sample X has 3 degrees of freedom. So it means sample Y, this is actually from UX because sample of degrees of sample because of the degrees of freedom. And a sample Y, UY equal times 6 because it has 6 degrees of freedom. If 6 it means 6 times 3 half, 6 over 2 or 6 half, 6 equal 3, if 6 half. 3 N K T or 6 half like this N K T. So next question. The temperature of sample X is now varied. On figure 3.1, sketch the variations with thermodynamic temperature of the root mean square RMS, speed of the molecules of the gas. I would like to using CRMS, CRMS as the speed of a root mean square. To sketch the variations of the root mean square of gas molecules with the thermodynamic temperature, we need to understand the relationship uh, that CR and S it equals square root of 3kt over n. Okay, this is for the RMS speed. Okay, and also you can writing as CRMS equal square root, sorry, square root of 3kt, 3kt over uppercase M. What is this? If you're using the molar gas constant, K is Boltzmann constant, R is molar gas constant, T for thermodynamic temperature with unit Kelvin, and lowercase m is mass of one molecule, and this one is molar mass. And to sketch this, we are going to start from the origin. Okay, and if you find the coordinate point between the thermodynamic temperature and RMS speed, you can find a strike line. We're connecting all data, all coordinate point, we have the strike line like this. Number 4, next question. State what is meant by simple harmonic motion. I have provided my opinion about this, my explanation about this. One, my briefly explanation. And let's continue to next question. A block is suspended from a spring as shown in figure 4.1. The block is pulled down and released at time t equals 0. It then oscillates vertically with simple harmonic motion. Figure 4.2 shows the variations of the velocity v of the block with height h of the base of the block above the floor. Okay, this is the diagram. And the question determine the amplitude in centimeters of the oscillation. The amplitude, we are going to use the information regarding the maximum height. The maximum height is 1. Okay, this is 9.5, and this one is 2, it is 3.5. Okay, we need this information to find amplitude. Okay, so the amplitude of oscillations is half of the total vertical displacement, so it is 9.5 centimeters minus 3.5 centimeters over 2, because half it is 3.0 centimeters, so 3.0 here. So that the angular frequency of the oscillations is 3.2 radian per second. Okay, so we will using the formula that omega equal v0 over x0. The maximum velocity is 9.5, just now I saw you, and the amplitude is 3.0 centimeters. So omega, it means equals 9.5 over 3.0, and it is 3.17 radian per second. Okay, or it is 3.2 radian per second. Calculate the period t of the oscillations. Okay, the period t equal 2 pi over omega, and it is 2 times 3.14, 6.2832 over 3.2. It is 1.96 second, 2.0 second. This is 2.0 second. On figure 4.3, sketch the variation of h with time t from t equal 0 to t equals 6 seconds. Okay, so we are going to start from the minimum value, the minimum point at when t equals 0. Okay, when t equals 0, h equal 3.5. 3.5. If 3.5 around, if here, I'm going to using it here, 3.5. And the maximum is 9.5, is 9.5 here, 9.5 here. And the period is 2. Okay, it means 9. If 2, the period, it means 9.5 here, and with 1, okay, it will be here. Okay, so one period, it means it will be back here, 3.5. So it should be like this. Is okay. Okay, and it's continue to 9.5 here, and one period continue to 2 to 4. Okay, continue to here, from 0 to 6. Okay, you can fix this graph on your graph. Okay, yeah, like this. Let's continue to number 5. State the relationship between electric field and electric potential. I have provided my answer for this one. And then two charge isolated insulating spheres X and Y are near to each other, as shown in figure 5.1. P is a point on the line joining the centers of the spheres. Explain why it is not possible for the total electric potential and the resultant electric field to simultaneously be zero at point P. Okay. I have provided my briefly explanations about this question. Okay. This is the first, and this is the second. I think this is clear. I will continue for the next question, part C. The magnitudes of the charge on sphere X and Y in figure 5.1 are Q and 2Q, respectively. The spheres may be considered as point charges at their centers. When P is a distance x from the center of sphere X, the electric potential at point P is 0. Show that the distance y of point P from the center of sphere Y is equal to x. Right. Okay, so spheres are treated as point charges, so we can use the point charge electric potential formula is phi equal 1 over 4 pi times epsilon 0 times q over r. This. And let's write the potential at point P due to each charge x and y. Okay, for potential due to x is phi x equal 1 over 4 pi epsilon 0 times x times q over x. Sorry. Okay, so it's going to be q over 4 pi epsilon 0 x. And the potential due to y, it is Vy equal 1 over 4 pi epsilon 0 times minus 2q, okay, over y. And it becomes minus 2q over 4 pi epsilon 0 y. And after that, the next step, Vx plus Vy equal 0. Okay. The electric potential at point P is 0. So it's going to be Q over 4 pi epsilon 0 x minus 2q 4 pi epsilon 0 y equal 0. So that multiply by 4 pi epsilon 0 over q, whether the left hand side and right hand side multiplied by 4 pi epsilon 0 over q. If you multiply, it's going to be 1 over x minus 2 over y equal 0. It's going to be 1 over x equal 2 over y. So it becomes y equal to x. Let's continue to part to state an expressions in terms of q, x, and the permittivity of free space epsilon 0 for the electric field strength Ex at P due to sphere x. It becomes, if Ex becomes 1 over 4 pi epsilon 0 times Q over x squared. So it's going to be Q over 4 pi epsilon 0 x squared. So answer here, Q over 4 pi epsilon 0 x squared. Determine an expression in terms of Q, X, and epsilon 0 for the resultant electric field strength E at point P due to the two spheres. Okay. From the previous solution, we have information that electric field, I would like to write it here, the electric field at P due to sphere X or S1 or Ex equal Q over 4 pi epsilon 0 x squared. And we have information as well that the distance y equal to x from sphere y to p. And after that, we have information also that charge on y is 2q. Based on this information, we are going to calculate the electric field at P due to sphere Y. So EY equal 1 over 4 pi epsilon 0 times 2q over y squared. So it becomes 2q over 4 pi epsilon 0 y squared. And we can simplify. Becomes uh, substitute this information, sorry, substitute this information into here. It becomes 4 pi epsilon 0 times 2x squared, or 2q over 4 times 4 is 16 pi epsilon 0 x squared, sorry, x squared. It's going to be simplify 1 over or q over 8 pi epsilon 0 x squared 1. So we can find E equal EX plus EY equal Q over 4, 4 pi epsilon 0 x squared. This is EX plus EY, this one, Q over 8 pi epsilon 0 x squared. Okay. We are going to set become the same denominator. It means times 2 for this fraction. 2Q over 8 pi epsilon 0 x squared plus Q over 8 pi epsilon 0 x squared. So it becomes 3Q over 8 pi epsilon 0 x squared. So this is E. So we can write in here the solution that 3Q over 8 pi epsilon 0 x squared. Next question, number 6. State what is meant by rectification of an alternating voltage. I have provided my answer to this question. This one. Part 2, state the difference between half wave rectifications and full wave rectification. I have provided also. And the difference between half wave rectifications and full wave rectification, when voltage wave form after rectification is, if half wave rectification, the wave like this, if half wave like this is the wave, and for full wave rectification, like this. Okay, so that's the difference. Half wave rectifications and full wave rectification. Complete figure 6.1 to show a circuit that produces half wave rectifications of an alternating input voltage V in to produce output voltage V out across the resistor. Right. So I would like to sketch the capacitor here. Okay. Like this. So this is the circuit. This P, this is N. So this capacitor state the purpose of this capacitor C in the circuit of figure 6.1. I have provided also, sorry, this is my answer, this one. Let's continue. The input voltage V in figure 6.1 is a square wave. Figure 6.2 shows the variations of V in with time t. So look that in this diagram that the maximum V or maximum voltage in is 12 and the minimum is minus 12. And in this figure 6.3 shows the variations V out with t with t times t. Okay, from the first V or the initial V is 12, and look, it decreased becomes 8 from 12 volt becomes 8 volt. The maximum energy stored in the capacitor is 0.041 joule. So this is the U max because for this question, show the capacitance of C is 570 mu farad. I would like to using the formula, and the formula is U max equal 1/2 C V squared. So now I would like to rearrange this formula. Becomes C is the subject. If C is the subject, the formula becomes 2 times U max over V squared. So 2 times 0.041 joule over 12 squared, because the maximum, just now I show you that the maximum of course is 12. Okay, and it decrease becomes 8. And if you calculate, the result is 5.694 times 10 to the power minus 4. Recall that 1 farad equals 10 to the power 6 mu farad. Okay, so I would like to convert, this is in farad, the unit. I would like to convert into mu farad. So I'm going to multiply by 10 to the power 6. 10 power 6 in farad. And it becomes 5.694 times 10 squared mu farad. And it is 569.4 mu farad, or it is 570 mu farad, like this one. Next question. Determine the resistance of R. From the previous information, we got that the initial phi is 12 volt and phi is 8, okay, and then T equal 0.01. So I will using the formula phi equal 0 e to the power minus T over RC. And it's going to be 8.0. Based on this information, 12.0 times e to the power minus 0.010 over R times 5.7 times 10 to the power minus 4. So that 8.0 over 12.0 equal e to the power minus 0.010 over R times 5.7 times 10 to the power minus 4. And if you calculate, this is 0.6667, but I would like to using logarithm or learn 0.6667 equal learn this number, e to the power minus 0.010 over R times 5.7 times 10 to the power minus 4. And we're going to continue to calculate this. Learn 0.67 is minus 0.4055 equal minus, if learn e to the power this one, it becomes minus 0.010 over R times 5.7 times 10 to the power minus 4. Actually, learn E, but learn E equal 1. and it's going to be minus 0.4055 equal, if you calculate this, is yeah, wait, I change, becomes R the subject, becomes R the subject, so it's going to be positive, negative and negative becomes positive. So 0.010, 2.3113 times 10 power minus 4. Okay. If you calculate this number, multiply by this number, it becomes this one, 2.3113, and times this one, 10 power minus 4. And if you continue to calculate, this is 43.27 ohm, or 43 ohm. Number 7, define magnetic flux density. This is my answer for this question. Next question, a long straight wire carries a current into the page as shown in figure 7.1. On figure 7.1, draw 4 field lines to represent the magnetic field around the wire due to the current in it. Okay. I would like to draw, to sketch first, second, the third, and the fourth. Now the direction based on the right hand rule, like this, the arrows. Okay. Okay. Next question. Two identical wires X and Y are placed parallel to each other. The wire both carry current into the page, as shown in figure 7.2. Explain why the two wires exert a magnetic force on each other. Is my answer. Continue. On figure 7.2, draw an arrow to show the directions of the magnetic force exerted on wire X. Label your arrow F. Okay, but I would like to sketch, to draw first. The actually the force is one, this to Y, and this is, yeah, this is F, label F, from X to Y. So this one, the magnetic, there are 4, 1, 2, 3, and this is 4, and the directions is on right hand rule. Okay, so this is the force from X to Y, towards Y from X. The current in X is double the current in Y. State how the magnetic force exerted on wire Y compares with the magnetic force exerted on wire X. That's my answer. The directions of the current in both wires is now reversed. State with a reason the effect of this change on the directions of the force on wire X. That's my answer. One. Let's continue to next question, number 8. A polycite of magnesium in a vacuum emits electrons when it is illuminated by ultraviolet radiation. State the name of this phenomenon. Photoelectric effect. For emissions of electrons to occur, the frequency of the ultraviolet radiations must be at least 8.8 times 10 to the power 14 Hertz. Calculate the work function energy of magnesium. So I will using this formula for the work function energy of magnesium. E equal HF. So H is Planck's constant and F is the threshold frequency. So Planck constant is 6.63 times 10 to the power minus 54 times 8.8 times 10 to the power 14, and it becomes 5.8344 10 to the power minus 19 joule, or 5.8 times 10 to the power minus 19 joule. So here, 5.8 times 10 to the power minus 19 joule. For ultraviolet radiations with a frequency of 11 times 10 to the power 14 Hertz, calculate the maximum speed of the emitted electrons. Now we are going to using the photoelectric equation that HF equal V plus 1/2 m V squared. And it is 6.63 times 10 to the power minus 34. This is the Planck constant, okay? And it's going to be times, sorry, I mean this one. This is the Planck constant, and F is 11 times 10, okay, equal 7.293 times 10 point minus 19 joule. So this is the Planck constant. So the kinetic energy maximum equal HF minus E, and it is 7.293 times 10 power minus 19 joule minus 5.8 times 10 power minus 19. It is 1.493 times 10 to the power minus 19 joule, or 1.45 times 10 power minus 19 joule. So the kinetic energy maximum becomes is 1/2 mv squared. Based on this information that kinetic energy maximum is 1, so 1/2 mv squared, so 1.493 10 to the power minus 19. So it is, I would like to arrange, n is 9.11 times 10 to the power minus 31 v squared equal 1.493 times 10 to the power minus 19 joule. So v squared equal 2 times 1.493 times 10 to the power minus 19 over this number, mass, 9.11 times 10 to the power minus 31. And if you calculate, the result is 3.278 times 10 to the power 11. So phi equals square root of this number, 3.278, 10 power 11, and the result is 5.73 times 10 to the power 5 meter per second. Next question. The frequency F of the ultraviolet radiation incident of the magnesium sheet is varied between 8.0 times 10 power 14 hertz and 11 times 10 power 14 hertz. On figure 8.1, sketch the variations with F of the maximum kinetic energy, Emax, of the emitted electrons. Use the space below for any working that you need. Okay, so I will sketch first the straight line from 0 to, I'm going to using different color. Fine. Okay, from 0 to, from the origin to 8.8, 8.8 around here, let's 8.8. Why 8.8? Because based on this, the information on that 8.8 on part B, I would like to remind you from about this number. Okay, the frequency of the ultraviolet radiation must be at least 8.8 times 10 power 14 hertz. And after that, the 8.8, if 8.8 on here, I'm going to continue with the positive gradient to 11 to the next coordinate point. Next coordinate point is 11, 1.45. This is 1.5 here, 1.45 around here. If here 1.5, so this is the coordinate point of 11, 1.45 times 10 power minus 14 hertz. Okay, so sketch the straight line from this 8.8 to here. The straight line. Yeah, like this. Let's continue. Oh, wait, I have to fix it first. This is actually minus 19, 10 power minus 19. Okay, because this number from kinetic energy maximum. Which one? Kinetic energy maximum. This one. 1.45 times 10 power minus 19. So this coordinate point 11 and 1.45 times 10 to the power minus 19 hertz based on this information that this is the axis for 10 power minus 19 joule. Next question, number 9. Fluorine 18 decays by beta plus emission with a half-life of 110 minutes. State the name of the beta plus particle, that is positron, so that the decay constant of fluorine 18 is 1.05 times 10 power minus 4 per second. Okay. Given that the half-life is T1 half is 100 minutes. Okay, 100 minutes. So if we convert into second, it means 100 times 60 seconds, and it's going to be 100, 110, 110. Okay, 110 minutes. times 60 equal 6,600 seconds. So we're going to use the decay constant formula, lambda equal 2 over the half-life. So it becomes a lambda, learn 2 equals 0.693 over 6,600 second. And if you calculate, the result is 1.05 times 10 to the power minus 4 per second. Determine the activity of 2.1 times 10 power minus 12 kilograms of fluorine 18. To calculate the number of atoms N, we're going to using the formula M over ER times U equal 2.1 times 10 power minus 12. It's 18 times 1.66 times 10 to the power minus 27. So it's going to be 2.1 times 10 power minus 12 over. If you calculate this, it becomes 2.988 and times 10 power minus 26. Okay. So after that, calculate this fraction, and it becomes 7.03 times 10 to the power 13 atoms. Okay. And then we're going to calculate the activity A. Activity A equal lambda times N, and it is 1.05 times 10 to the power minus 4 times 7.0 times 10 power 13, and it is 7.35 times 10 power 9 becquerel, or it is 7.4 times 10 power 9 becquerel. So the answer here is 7.4, 10 power 9, becquerel, ready. This is the unit. Next question. A small sample fluorine 18 injected into the body acts as a tracer for use in medical imaging. Describe how the interactions of a beta plus particle with an electron in the body enables the formations of an image. This is my briefly explanation. Next. Suggest why 110 minutes is a suitable half-life for a nuclide used as a tracer in medical diagnosis. And this is my answers. Next question, number 10. Explain how redshift leads to the idea that the universe is expanding. I have provided my explanations about this question. One. Next question. Stars in a distant galaxy emit radiation. The total luminosity of the stars in the galaxy is 1.90 times 10 power 36 W. The emission spectrum of the radiations contains a line X at a wavelength of 658 nanometers nm. Radiations from the galaxy is observed on the Earth. The observed radiation has a radiant flux intensity of 8.42 times 10 power minus 16 Wm power minus 2 W over m squared. In the observed emission spectrum, line X is at a wavelength of 726 nm. Determine the distance d of the galaxy from the Earth. I will using this formula F equal L over 4 pi d squared. And I would like to rearrange this formula because if we will find distance, we are going to set d becomes the subject. So it's going to be d squared equal L over 4 pi times f, or d equals square root L over 4 pi times f. This. Now substitute all information into d. D equals square root. L is 1.90 times 10 power 6 over 4 pi times 8.42 times 10 power minus 16. And continue to calculate 1.90 times 10 power 36 over 1.057 10 power minus 14. The root 1.797 times 10 power 50. And the result is 1.34 times 10 power 25 meters. So distance is 1.34 times 10 to the power 25 meters. The unit is meters. Next, the speed phi of the galaxy relative to the Earth. Right. So you can calculate the speed or phi. I'm going to use the redshift formula for non-relativistic speed that that delta lambda over lambda equal phi over c, which delta lambda is lambda action minus lambda 726 minus 685, 658, sorry. And if you calculate the result is 68, and the unit is in nanometer, nm, okay, and after that substitute into this formula. If you substitute, it becomes, I would like to rearrange first. It becomes phi is the subject, delta lambda over lambda times c. This substitute into this formula. So it becomes 68 nanometers over 658. This is lambda times c. C is 3.00 times 10 power 8. And the result is 0.10334. 00 times 10 power 8. And the result is 3.10 times 10 power 7 meter per second. So the speed is 3.10 times 10 to the power 7 meter per second. This is the speed at which galaxy is receding from the Earth. Find this number. Next question. Observations of many galaxies, such as the one in part B, lead to many pairs of values of D and Phi plotting that values reveals a trend. On figure 10.1, sketch the variations of Phi with D. Right, this graph is a straight line graph with the gradient, or I'm gonna using this formula, the formula that phi equal h o d. H o is h0 is the h0. This one is the Hubble's constant. This one is the Hubble constant. D is distance, and phi is the resistance velocity. So the gradient is of this. This is the straight line actually from origin, the straight line. But the gradient, okay, and the gradient is phi divided by d. Phi divided by d is h. Also, phi divided by d. This is the Hubble constant. So how you gain the gradient, or m? M is the Hubble constant. Okay, phi over d. Question: state the name of the quantity represented by the gradient, Hubble constant. So